Hello, my name is Sunny, and welcome to the first video in a tutorial series that will take you from knowing very little about the Ethereum platform to being able to develop and deploy smart contracts. I'd like to go ahead and give a thanks to the Blockchain Training Alliance and Finago. Throughout the course of this video, we're going to be looking at how decentralized applications run on the Ethereum virtual machine. We call decentralized applications dApps for short, and we abbreviate the Ethereum virtual machine to the EVM. We're going to be doing a quick overview of blockchains, looking at a diagram of a block, and distributed ledger technology overall. We will be taking a look at the hashing cryptography that goes behind making blockchains so secure. We will be looking at what Merkle trees and Merkle roots are, and even making our own Merkle tree. We will be using a few use cases throughout the course of this tutorial series. For one, we will learn how to create a token on Ethereum. Ethereum allows people to create these custom tradable assets between one another called tokens, much like how you can send Ether back and forth between wallets. We're also going to be learning how to create something called an ICO. It stands for an initial coin offering. Basically what this is it's a crowdfund or a crowd sale that uses these custom tokens, allowing businesses to kickstart an idea using this crowd sale. People can just send Ether into your ICO contract and be able to purchase these custom tokens. So here we are on the ethereum.org page. If you're not too familiar with what Ethereum is, it's basically blockchain 2.0 if you look at Bitcoin being blockchain 1.0. Where all the Bitcoin network offered was for people to carry out these transactions of Bitcoin between different wallets and addresses. What Ethereum offers is something called the Ethereum virtual machine. Basically, every machine running an Ethereum node has access to this global virtual computer called the EVM. What the EVM allows people to do is write secure snippets of code called smart contracts in a language called Solidity. These smart contracts are secured on the blockchain and completely immutable, meaning people can't go back and change them. As blocks are constantly being confirmed onto the blockchain, it becomes harder and harder to change the blockchain over time. Here we have a simple diagram of the Bitcoin blockchain. As you can see, we have three blocks right here, block 1, 2, and 3. If we look at block 2, for example, we see that it's comprised of a hash of the previous block's header. This is true for every block in the blockchain. As you can see, the blocks are reliant on the previous blocks. This goes all the way back until the very first block in the blockchain called the Genesis block, which is hard-coded. So these blocks rely on the headers of the previous block and something called a Merkle root, which contains all of the transactions for that block. I'll show you more about a Merkle root when we get into Merkle trees and how to make them. To understand what a hash is, here we have a SHA-256 hash generator. A hash is basically a one-way encryption that allows you to encode any piece of data. For example, I can enter some unique text below, and every unique piece of text I enter will give me a unique SHA-256 hash. Let's go ahead and try this out. The hash for WASD is this string of characters right here. If I change one character, for example, if I add a D, I get a completely new, unique, different hash. If I go back, it's the same thing I had before. If I change one of these characters, say the 3, it gives me a new hash for when I replace the D with the 3. When I put back the D, we return to our previous hash. Using this principle, we're able to create something called a Merkle tree. This is a diagram of a Merkle tree, and as all trees do, it has a root called the Merkle root. So H sub A, H sub B, and so on stands for the hash of transaction A. So here's a list of transactions A through P. The hashes of transactions A and B are combined and hashed together to create a hash for transactions A and B. To show you what I mean, let's go ahead and create some transactions. Let's say, for one, Bob sent Sally 10 Ether, which is the currency for Ethereum, much like Bitcoin has, obviously Bitcoin. So Bob sent Sally 10 Ether. This is our hash for Bob sending Sally 10 Ether. Let's go ahead and just put that in a tab. And we can go ahead and create another unique transaction. Jake sent Kyle 3 Ether. And we have another unique hash. So as you can see, we have this hash for Bob sending Sally 10 Ether, and this hash for Jake sending Kyle 3 Ether. What we can go ahead and do is copy and paste these two strings together to create a new hash of the combination of the first two hashes. So here we have our hash of the combination of the two transactions of Bob sending Sally 10 Ether and Jake sending Kyle 3 Ether. Now that we have this combination of transactions, let's go ahead and make two new unique transactions. If we go back to our Merkle tree, we've already created transactions A and B, and we also have our hash for AB. We're going to go ahead and create C, D, a hash for C and D, and hash AB and CD together to create a small Merkle tree for ABCD. So let's create two new transactions. Jimmy sent Andrew 7 Ether. And Susan sent Emily 1 Ether. Now let's go ahead and combine our hashes for transactions C and D. And here we have our unique hash for transactions C and D together. Let's go ahead and combine that with the hash for transactions AB. And as you can see, here we have our Merkle root for the 4 transactions.